So welcome to the seminar for the people who has joined, and for the people who will see it later. We are happy to have Professor Shiwen Mao, okay, who is a professor at Auburn University. Okay, he is an IEEE fellow, distinguished lecturer by ComSoc. A very known scholar in our field. He has a PhD from Polytechnic University, okay, New York University now, and from Brooklyn from 2004. Okay, and he joined the Auburn University in 2006. Okay, holding several positions and chairs up to now. Very wide experience in editorial boards, okay, and receiving many distinguished awards from the Communication Society and for Best Paper Awards. As I said, he is one of the pillars, let's say, okay, of the Communication Society. Okay, we all know of his work, and we are happy that he accepted our invitation to be here with us today in our CSIM seminar. So, Prof. Mao, thank you again for accepting the invitation. Please, the floor is yours.
Yeah, thank you so much for the introduction, and thanks Nizar and Luca for host my talk, and it's really a great honor to be able to talk to CSIM members, and I really appreciate. The topic of this talk is a little bit different from the traditional, like people, networking people, wireless people. We talk a lot about 5G, 6G, 5G beyond, the next generation wireless networks, architectures, virtualization. But so this is more like on the application side. So it's about the near field communication technology, RFID, and use that for sensing, for radio frequency sensing, for monitoring and detecting of this human pose. It's like a skeleton, the skeleton of a human body. So so it's more like a RF sensing application. Okay. This is joint work with my student Chao Yang, Lin Xiaowan, and Shiwen. So here's the outline. So I'll start with some preliminaries and a review of some existing interesting approaches, okay, to address the problem. Then following that, I will talk about 3 pieces of work. The first one is to make it work. So to use RFID to monitor this in real time, this human pose. And the second part is how do we generalize. The second part and third part is how to generalize a trained model. In particular, the core of the model is a deep learning model. How to generalize this to different people and different wireless environment. Okay, so if you work in the wireless communications and the networking area, you know, for wireless signal propagation, if the location is changed or the environment is changed, then the channels, then the propagation will be very different. So that is a big challenge for applying deep learning to machine learning to networking wireless problems. So here we need this kind of generalization, okay? And eventually I'll conclude the talk, some observations. Okay, so so this talk is focused on human pose tracking. Okay, so it's an important part of this human computer interaction. So as illustrated in this picture, so we can capture the human body with a video camera, okay? Then we remove all the backgrounds and the details, then we represent the human body with a skeleton. It's like a matchman, okay? And so this has been there has been a lot of applications, okay, for this, okay? One is that human computer interaction, so you don't need a keyboard or a mouse or whatever to input, to control your computer, like somatosensory games. Okay, so we don't need wire anything or hold a remote, but we just act in the space. Then we can control the video game. Another example of application is this in the middle. Okay, these pictures is a movie. Okay, making movies like yeah, like one example is this Avatar movie. So the actress wears these sensors, then act in front of a screen, a green screen. Then the skeleton is extracted. Then you can add on replace the human body details, but with some other details. Then you can create this avatar movie, like the natives of the Pandora planet, right? So, or this can be used for like a sign language interpretation and gesture recognition. Yeah. So, yeah, it has been this problem has been active for a few years and a lot of interesting work there. So the general trend is like we're moving from 2D to 3D, okay, and this human pose, and also from single person to multiple person. Yeah, the traditional technique is based on video camera, so we capture video, okay. So, but like in these examples, okay. But there are the performance of this video-based, camera-based approach is limited by this illumination. So basically lighting. Okay, we need a sufficient lighting to recognize the human body, and also we need it will be better to have a clean background, like a green curtain, right? So like here we are using WebEx or sometimes I use Zoom. So if you want to replace the add a virtual background, okay, so then if your computer is not very fast, then Zoom will ask you to put a green curtain, then at back, then you can cut your body, your head from the background, then add the virtual background, something like that. So basically this cluttered background will affect the performance, and also the camera angle. Okay, so if it's like above your head or in front of you, so that will make a difference. Yeah, one issue with a camera-based approach is this security and privacy issues. This is a news I found published on June 29th this year. So basically shows many video cameras, webcams that has been security cams have been keep on streaming your daily activities on the internet, so people can get hold of it. Yeah, so that is a big concern of all this camera-based approaches. Okay, so so to this part, then to this end, then radio frequency sensing that has the unique advantages, like we don't need lighting. Okay, so it's a radio wave. Okay, so we don't need any light, and it's less intrusive. So with we are under the exposure to Wi-Fi signals everywhere, so every day, daily. So you exposed to like a radio wave is less intrusive than having a video camera looking at you all the time, right? So also it doesn't, because the radio signal can get around the obstacles or penetrate walls, so it doesn't require like a video camera base. It doesn't require this line of sight kind of condition. Okay, but there are many challenges. One is this here is we need to extract motion features from features related to motion from these radio signals, received radio signals like phase and phase or frequency change or amplitude, that kind of information. And then we need to map this extracted these radio frequency features to a human pose, okay, skeleton. And sometimes it's easier. It's always easier if the subject is not moving. So it's a static kind of person. Okay, it's a subject. But it's more challenging if the subject keeps on doing some activities. It keeps on moving. Okay, and also because the video, the radio signal is propagates through the open air. Then we will always need to deal with this interference from the environment. So there are two types. One is the other users using the frequency transmitting interfere with your radio signal, and a second type is the movements, okay, of other people or other objects in the environment. They will cause the change in the environment and cause interference as well. Okay, so a promising technique is we call it multimodal learning. So basically, it's a vision-aided approach, assisted approach. So like shown in this figure. So for the same activity, same subject, we capture radio data using antennas. Okay, but simultaneously we also use a video camera like a Kinect to capture video data. The video data, vision data, can serve as a labeled like a data to help the training of this deep neural network that takes this radio frequency data as input. Okay, eventually. So basically, the training is assisted with this vision data. Okay, but once the model is well trained, then we don't need vision data. So there's no for inference. So there's no privacy concerns here. Okay. And existing systems have been developed, built based on this FMCW radar. Okay, it's a frequency modulated continuous wave radar, Wi-Fi, millimeter wave, etc. Okay, so I will review this prior work quickly in the next few slides. So the radar-based approaches, it has a lot of advantages. It's quite accurate. Okay, it's capable of tracking multiple subjects, multiple people. Okay, it works here. So there's this images. Okay, so cameras that capture the human body, and that is used as used to train the learning model, okay, CNN model, okay. Then the captured radio data is organized in the form of tensors. Tensor is like a higher order kind of matrices, okay, so like 40 tensors. Then there is this RPN, it's a region proposal network. It will zoom in to identify the area for each person. There are could be multiple subjects. So first you zoom in to identify the region corresponding to one person. Then this CNN will be used to recognize the gesture or the pose of this person. Okay, so and it works with in the case of through wall detection. So the behind the wall. So that is a unique advantage, but the system is very complicated. It's implemented with this USRP, software-defined radio platform, and it requires a lot of this T-shaped antenna arrays. It's one picture is shown here. So each of these triangles is an antenna element. So, and it requires a lot of calibration for synchronization for where to place the antennas. Yeah, if you have any questions, please feel free to just ask and stop me. So yeah, and so there's a Wi-Fi based techniques compared to the radar systems. Then Wi-Fi is commodity devices and it's low cost. The hardware is low cost. Okay, and it works like also from the MIT group. So it works with the Wi-Fi is also less intrusive than with the camera. Okay, and a wide range because Wi-Fi is 100 meter, 200 meters range, so you can the range is big, so you can cover a large area, and it works for 2D and for multiple people, and 3D for single people. But Wi-Fi is because of the wide range is sensitive to interference from testing environment. Okay, so no other movements. Okay, otherwise then there will be interference generated. Also, you can see this Vicon camera systems. This are very expensive. Okay, so we try to we were working on like a localization problem for UAV flying in an indoor in a warehouse, but it's very difficult to get the ground truth. We cannot afford this Vicon system to get the ground truth of the 3D the exact location in a 3D space. Okay. So we found the RFID is a very good, nice solution. Okay, so as a low-cost wearable sensors. Okay, so these are the text. Okay, so pictures of a text shown here. So there's a microchip in the center, in the middle, that carries a unique ID. It called the EPC code. Okay, so from like 96 to 400 plus bits, you can store in this microchip. And the microchip also store the code, the algorithm for this interrogation procedure for collision avoidance, etc. And then these are the antennas. Okay. So it is a radio wave-based identification technique, and so here in the lower part of the slides, then it shows the three parts of our RFID system. Okay, on the left-hand side, there's these are the tags. Okay, the tags can be pre-made, like very cheap, 5 cents, 10 cents. Then or you can print it. Okay, you can write code into this microchip and print a tag. Then the tags can be attached to the boxes or objects. Okay, the tags are interrogated by a reader. Okay, using an antenna. Okay, then the reader can be handheld or mobile or fixed. Then eventually the captured data is stored or analyzed by a computing system, a computer. So historically, there's a lot of communication-based applications we call. So the idea is that so here in this picture, so this yellow part, this is a microchip. Okay, it stores this electronic product code, EPC code. So for this kind of applications, is that you use a reader to interrogate to query this code, this tag. The tag will respond with the EPC code it stores. Okay, so it's based communication. Okay, successfully transmitting and decoding this EPC code. Once the reader receives this EPC code, then it can uniquely identify this tag because this EPC code is unique in the whole world. Okay, and so this can be used for like person identification. Okay, like a easy pass, or so this picture is like a sport, like a marathon, like a game. Okay, so basically you have thousands or tens of thousands of runners. Then how do you accurately keep timing? Okay, for each athlete, each runner. Okay, because it may take 30 minutes for everybody to pass the starting line, right? So then the idea is to put that tag on your shoes or on the chest. Then when the runner passes the starting line, then this tag will be read and the time stamp will be recorded. Okay, so people also use RFID tags as an implant. Okay, in your hand, then you can use your hand with your hand to start your car, to open unlock a door. So the basic idea is communications will deliver, query the tag, and if effectively successfully decode this EPC code, and then you can identify the tag. Okay, then there's also a lot of sensing-based applications, especially in recent years. So the idea is that we query the tag, then the signal will propagate through a distance. Then at the reader side, we can read the phase angle of the received signal. Okay, so that is a function of the distance the signal propagates. Okay, propagated, and some other things like these offsets, phase offsets, and also the frequency or wavelength. And by examining this phase angle, example the phase angle, then we're trying to recover this distance. Okay, but this distance is buried in a lot of noises and offsets. So, but if you are successful, you can translate this phase angle to distance, then you can do like a vital sign monitoring. So that is a monitor. We will put the tags on the chest of a subject. Then we can monitor the up and downs of the chest. Okay, then we can recover this respiration signal, and also indoor localization and many like gesture recognition and many other applications. So this kind of class of applications is focused on this wireless channel. Okay, yeah, we want to see what happens during the propagation of this signal through the channel. We don't care about the EPC code anymore. Okay, then like a phase angle, Doppler frequency, and this RSSI, then we can sense a lot of things. Okay, so
Professor Mao,
yeah,
can I have a small question?
sure.
So that means how many sensors we will have on the human body, or what do you expect that there will be the number if you would like to capture all of these gestures?
So yeah, that's a good question. So it depends. Okay, so like here for the talk, we that in the following slides, we actually put a 12 tags and one tag on each joint of the body. But sometimes you don't need that many. Okay, so it's like so when the tag number is small, then sometimes you don't get some good examples because the location of the tag. So you query it, it doesn't respond to the query. Okay, so there's a lot of lost examples. So that is bad. But when you have too many tags, and like an tag array, when they're placed closer to each other, then the tags will interfere with each other. So when one tag is queried, it generates a response. Then its response will also be received by its neighboring tags. Then these neighboring tags will generate their response. So it's like a bounce back and forth. You have an infinite sequence of this decreasing response added. So that is called that is bad. So too many tags could also be bad. So that is a design factor you need to try and control. Yeah.
Thank you.
Okay. Yeah. So basically, for the second class of application, is a sensing application. So we can use this RFID tags as wearable sensors. Okay. So they can also, like shown in this picture, you can put it weave it into your clothes. Okay. Then it doesn't have to be attached to your body, but to the clothes you wear it, or blankets, so a hat, yeah, a glove. So then you can you can make good use of it. Another advantage is there's no power consumption. Okay, so it's battery free, it's passive tags, so it can last forever. Okay, you don't need to recharge or replace batteries, and it is near field communications. So it's the entire this query response between reader and tag is more resilient to the interference from the environment. Okay. So the idea is use text as wearable sensors. Okay. There has been some interesting work already. So, like here, the RF Connect. Okay. So the basic idea is that you put this RFID array, okay, attached to the human body. Then you detect the angles, okay, of between different arrays using a technique called a hologram. Okay. And this RF Connect is also assisted by this video camera, okay, vision data, okay, to detect this angle of the arm. Okay. So but the limitations are like you to monitor the entire body, probably you need a lot more text, and also the to build this hologram map is hard. So also, if the subject is changed, the environment is changed, then you need to rebuild this hologram. And so this multimodal learning that here using this both vision data and RF data is helpful. So in the following slides, I will introduce 3 pieces of work from my group and done by my students. So the first part is how to make it work. So how to make it work using this 12 tags attached to the human joint, so we read the text, then we can recover the human pose. Okay. So the system is shown here. So we put the shoulder, we put tags. Okay, these are the UHF off-the-shelf like RFID tags, like operating in the 900 megahertz range. So we put the tags on the shoulder, chest, pelvis, and knee, and wrist and elbow, Then the system consists of this RFID reader that is here. Okay. Then it operates with 3 antennas. Okay, so but these 3 antennas are not operating in parallel. Okay, so they operate sequentially. So because the tag may be at a different location, out of range of one of the antennas. Okay, so this is 1, this is 2nd, and third 3 antennas. These white blocks, white panels, and this black box is a Kinect 2.0. So that is capture the video, okay, the motion in video motion of the human, and we use that as label the data to train the machine learning model, okay? And then there's a computer to process all the data. So then what are the challenges, right? So you can see here we have 12 tags attached to the human body. Then we query these tags to collect the phase angles, okay, of the received response. So here we plot the response from one of the tags, one of the 12 tags. So the y-axis is the response, the phase angle in red, and the horizontal direction is time. Okay, so you can see there's the data is very sparse, and it's noisy. Okay, so in particular, you can see here there's a jump from this very low value to 2 pi. Okay, close to 2 pi. So that is caused by this modular operation. Okay, that there's a wrapping the phase within to cut it within 0 to 2 pi range. So there's a big jump there, and also you can see another the second part here. There's also a big gap here between in this at this time. So that is caused by frequency hopping, because the FCC requires the frequency hopping for all the RFID systems in the US market. So the reader will hop among 50 channels, okay, in the 900 megahertz range. So 200 milliseconds, then it jump to another channel, then 200 milliseconds, it jump to another channel. So then each time there's a jump, okay, the change of the operating frequency, then here this FS will change. And also this phi S0. This is the channel hopping phase offset. So each time there's a different random different kind of phase offset introduced, and the frequency also change. So there's a big gap there. And the third part here is you see there's a lot of zeros. So those are the missing data. So because we have 12 tags. We have 12 tags attached to the human body, so then 3 antennas, but they were operating sequentially. Okay, so and the tags, when we shoot a query signal or interrogation signal to all the tags, then they need to avoid collision. If 2 tags respond simultaneously, then there's collision, and then the reader cannot decode the signal, right? So there's a kind of slotted aloha or like a kind of a MAC, media access control protocol, collision avoidance, like kind of protocols implemented for the tags. So anytime for a query, there's at most 1 tag that will respond. Okay, so then the consequence is that so we have a lot of zeros missing. Okay, so missing examples. We cannot have a continuous sequence of examples. So if we organize the tag response in a 3D tensor form, okay, so one dimension is a text. We have 12 tags, so 12 kind of these slices, and the vertical space we have 3 antennas. Then the horizontal direction is the time, okay, time slots. Then you will see that in each this vertical, so for 12 tags and antennas, so each time slot, we can have at most 1 sample from all the tags. Okay, so that is so this RFID data is very sparse. Okay, so that means we have 35 empty blocks, okay, among these 36 positions in each time slot. So it is very sparse. Okay, so then the question is how to make use of this such a highly sparse data. Okay, so the system design is like this. So the first step is to deal with these distortions. Okay, so that is shown here, like offsets, disrupt phase offsets. Okay. Then we deal with we use some techniques from our prior work. Okay, so first we need to estimate and this hopping. We use a reference channel. We translate all the measured samples from a channel to a reference channel. Then we estimate the offset frequency, channel hopping offset, and then remove it. Okay, then we also deal with these wrapping offsets. Then the next part is data imputation. So we use a technique called this high accuracy, low rank tensor completion. We use this technique to estimate all the missing, all the blank, this as shown here, all the blank blocks. Okay, then eventually we get 3D tensor with all the elements estimated. Okay, some are measured. So some are estimated. Okay, so one example is shown here. You can see this missing data is recovered by this high accuracy, low rank tensor completion technique. Okay, so but another challenge that is a big challenge is this how to construct a human pose from this very sparse and very small amount of samples. Okay, so because the RFID system was initially designed for like a warehouse, or you check how many shoes, how many jeans you have. So it's not designed for automation. So the sampling rate is quite low. It's 110 hertz. Okay, so in every second you can get 110 phase samples. Okay, but we need to reconstruct if we want to monitor this human pose in real time. Okay, so basically we are reconstructing a video with a human pose. Okay, so suppose we have a moderate goal of to get this confidence map video at 10 frames per second. So then we only have 110 face samples, okay, per second. So that means we only have 11 face samples we can use to reconstruct a human skeleton, this image. Okay, so yeah, even if the image is a very low, has a very low resolution, like 100 pixels times 100 pixels, then that means we need to use this solve for the values for this 10,000 pixels using these 11 known samples. Okay, so this is a very severely ill-posed problem. Okay, the solution to this problem is that we use this forward kinematic technique. So rather than just construct estimate a video, okay, a human skeleton video from this 10 frames from these 110 samples. Okay, so we actually estimate the new location of each joint. We want to estimate the location of these 12 joints. Okay, so and we actually estimate the location of each joint based on two things. One is the 3D rotation of this joint, this limb, this part of the body, and the second is the parent joint of this part of the body. Okay, so then the 3D rotation of this each joint can be represented in the form of a unit quaternion. Okay, so it's written here. So we only have 4 parameters, R, X, Y, Z. So for the 12 joints, then we only have 48 unknown variables. So that's a great reduction from this 10,000, okay, to 48. So then if we find the solution for these 48 parameters, then we can reconstruct recursively, okay, from the root joint position. Then we find it's a child, the new position of its child joint, and so forth. Recursively, we can recover we can estimate the position of all the joints. Okay. So this is done with autoencoder. Okay, so a variational autoencoder. It's a deep learning neural network. So this is the view of this unfolded over time. So here each column so corresponding to one time instance. Okay, then this is the next time, so forth. So initially we have RFID data. So that is fed into this autoencoder, these two blue blocks. So we have a encoder that extracts the features, latent vectors, variables. Okay, then the decoder will reconstruct the input using this from this latent variables. Okay, so the purpose for this part, the goal for this autoencoder is to extract this rotation features from the RFID data. Okay, so then these cues are the unit quaternion. Okay, so that is representing the here the unit quaternion, representing the rotation angle, 3D rotation of the human body, human parts, okay, limbs, and then etc. Then we adopt so as shown here, so we have this parent joint, then this is the rotation angle. Then that is this recurrent autoencoder, so that is translate this RFID data to unit quaternion. Then we have this FK layer, so let's forward the kinematic layer, so that will translate this rotation matrix. We already know the 3D rotation of each tag, each joint. Then that is translated further to a 3D pose. Okay, so that's shown. Then we use this Kinect data, this video data, as labels. Okay, to use that to train this model. And also we use that for performance evaluation. So that as a ground truth to measure application errors. So this is the system overview. Yeah, I think I have discussed all of this. So basically, we capture RFID data through three antennas, and simultaneously using a video camera. Okay, so then the captured video camera will be video data will be used as a ground truth, okay, for training and for performance evaluation. Then we calibrate this RFID data. Okay, so we deal with the noises and offsets and and we deal with the sparse data by using tensor completion to estimate the missing data. Then this is fed into this deep neural network, and then we can recover the 3D skeleton. Okay. Here is the pictures from two of our experiments. The first one, this is my student Chao Yang. He's wearing 12 tags and standing in front of the three antennas. So this is one. This one is he's standing still, and this one he's walking, but not forward, but in the same location, but walking. Okay, so here is the real time estimation results. For while he was walking. Okay, the blue skeleton was recovered from Kinect video data that is serves as a ground truth, and the red skeleton that is estimated from RFID data. You can see it is quite it works in real time and it is quite accurate. And here are more results for squatting and the twisting, body twisting. Okay, so you can see the both the ground truth and the recovered pose using RFID data. Okay, so how about the numerical performance, right? So in this figure, the upper right corner, this figure, we plot the distribution, error distribution. It's a CDF, cumulative distributing function. Okay. So for one is the blue lines for one limb, or just one arm, okay, or leg motion, and the red line curve is for the complicated motion, the full body, okay, all body parts are moving. So the median error has 50%. So location error is like a 2.8 and 3.7 centimeters. Okay, so it's quite accurate. And we also, in the lower left of plot, we show the error, estimated errors for this 12 joints. Okay, so and here we show the errors for different activities like twisting, squatting, waving, kicking. Yeah, and here we try the in the table is the mean average estimation error collected for in different environments, like in different computer labs, empty corridor, living room of apartment. Okay, so basically you can see the average error is less than, is around 4 centimeters. Okay. Then so basically the first part we show it works. Okay, so then what are the problems here? So that this is a general problem of all wireless, if you want to wireless communications networking. Okay, so it's the change in the environment. Okay, that causes change in the propagation environment, changing in channel. Okay, so in this experiment, we show the estimation error. Okay, so for different subjects. Okay, so subject 1, 2, 3, 3 different students. So these three are trained. So we first collect data from these 3 students and train the model, and apply the model to these 3 students. So the error is like 3 to 5 to 4.5 centimeters. But if we apply the trained model to subject 4 and 5, they are untrained. They're new student with different height. Okay, different body kind of skeleton. Okay, then the error will be bigger. Okay, and another similar situation is that we train the same person, but in 3 locations. Okay, Then when we we have this 1, 2, 3, 4, 5, 6 different locations. Okay. Then the error is given here. But if we apply the trained model to different locations like 4, 5, 6, and you see the error will be like almost double. Okay, so that is the next part we want to deal with. Okay, so the first part we deal with is subject adaptability. Okay, so we train model to with data from some student, then we can apply it to some different unknown, untrained kind of subjects. Okay. Just a second. I think I saw some questions, but yeah, maybe
Yes, there have been actually some questions, but we thought that maybe we delay them until then. But if you want, I can tell you now the question.
Sure.
So, do you prefer now or at the question and QA session?
Yeah, I'm good either way. So shall I?
As you wish. So as you said that there are questions. So yes,
Okay.
there is one question that says in page 11, the number of tags affect the system performance.
The question is the answer is yes. So basically, we imagine this this human pose, right? It consists of like it can be represented by this 12 joints, but you can go more. You can put one, two more on the feet, right? On the foot, left foot and the right foot, or you can put one on the head. So the more the impact of number of tags is one is that if they spread out into a larger area, then you need more antennas to cover them, because the antenna is a directional antenna. It only covers a small region in front of the antenna. So that's why for the 12 tags we have 3 antennas. Another one is that if the tags are close to each other, then there will be this it's called a mutual coupling. So basically, the response of one tag will generate a further response from its neighboring tags, and then it's like bounce them back and forth. That will cause a lot of interference to the response signal. So yeah, so sometimes you see like a curve like this. So when the number of tags is small, the performance is bad. When the number of tags is too many, then the performance is also bad. So there's some good numbers. Yeah.
Some optimal point of sensors, let's say.
Yes. Yeah.
There is another. Good. So there is another question that says, do you see issues in the presence of several bodies or other tagged objects?
Yeah, good question. So this is the one advantage of this RFID technology, because it's a near field communications. The range is small, so and maybe like a square meter, one square meter. Okay, so range. So yeah, in such a small range, usually you don't have too many people.
Yeah.
Right. So if it's like a out of your arm's reach, there's another people subject moving there. So that basically does not affect your test experiment much. But it's a completely different case for Wi-Fi. So if for Wi-Fi, if somebody else is moving in the room, although it's very far from you, then that will also cause interference to the test. Yeah.
Yes. And the last question on the chat is, are there limitations on capturing fast-moving bodies?
We haven't tried different speed of the activities, motions. So we just tried like a normal, like a, yeah. I think the question is like your fast forward your YouTube playing your YouTube video, then so basically when because the RFID sampling rate is fixed at 110 hertz. So if the motion is fast, then you see the discontinuous motion of the
sampled one
from this skeleton. Yeah.
Okay,
That's my
okay.
guess.
So, yeah.
Okay.
Thank you for answering the questions.
Okay.
Please, the floor is yours.
Sure. Okay. Thank you. So yeah. So now the question is, how do we deal with we train a model with data from 3 subjects? Then how do we apply it to some unknown, untrained subjects, but still get a good performance? So that's the question. Okay. So one easy way to solve this is that you collect all kinds of different data, okay, from different people, tall guy, a short guy, and then use all these different kind of human skeletons to train your model. Then you can then your model will know all these different kinds of skeletons. Then you will perform well. Okay, but it is very costly to capture so many so much labeled data. So we propose to do this. So basically, in the RFID-Pose system, we use this initial skeleton. So that is the height of the people. Okay, so then we can estimate this the length of this limb. Okay, each part of the body. Okay, this is used as input information in this decoder, recurrent decoder, and this FK forward kinematic layer to reconstruct this human pose. Okay, so the training in this in the previous system, okay, is like shown here. Is like this. So we have paired. We call this FK layer, the input to the FK layer. We call it this target skeleton, and the input to the decoder, we call it the source skeleton. So these are paired. It's the same. Okay, we use the same. So the idea here is that we want to use a different. We want to couple this. So we use different source initial skeleton in the recurrent decoder. And then we use a different target initial skeleton in the forward kinematic layer to reconstruct human pose. Okay, so that is illustrated in this figure. So basically, we do not pair them. Okay, so we break down this dependency here. So hopefully, then we can get good results. Okay, so that's the idea. So here is an example that so we have the same, it's the same video frame rate, okay, same kinematic connect this video frame rate, sampling rate, same moving speed, but different subjects. Okay, this is subject 1, the first row. The second row is subject 2. Then you can see the pose are quite different. Okay, so that is the issue we need to deal with. Okay, our proposed solution is to use a self-supervised network, self-supervised model. Okay, so it's a cycle kinematic model, or we sometimes called cycle consistent network model. Okay, so the idea is that this part is the original part from RFID-Pose. The difference is that we use different skeletons. Okay, so in this forward kinematic layer and in this decoder layer, and the difference here is that we add a cycle here, add a loop here. So first we have RFID data, then that pass through this autoencoder, then we recover the unit coordinate data. Okay, then to represent the 3D rotations of the human body parts, and then we feed this back into another, we call it backward, okay, recurrent autoencoder with a B here. So that will reconstruct from these coordinates, we will reconstruct the fake RFID data. Then we compare the errors, okay, as a loss function, the difference between this input RFID data and this reconstructed RFID data. We call this cycle consistency loss. Okay, then once the 3D pose is reconstructed, then we calculate the position loss. So basically, that's a difference difference in the 3D positions in each human joint, okay, between the reconstructed skeleton and also this video ground truth skeleton, okay. Then we also use a neural network. I think it's shown here. Yeah, we also use a neural network, okay, to call it a discriminator network to determine the difference between these two. Okay, we call it the adversarial loss. So the purpose for this part is that this will tell us if the model is well trained or not. Okay, so basically we add this loop cycle consistency network model part, and we introduce this cycle consistent loss, and we also have position loss. We also have adversarial loss. Actually, in the paper, we also talked about smoothness loss. So basically, human body's movements is continuous. It will not jump. Okay, so jumping in space and in time. So basically, there's some kind of smoothness constraints there. So that is also considered. Okay. So I think I have skipped this. So let's see some results. Okay, so again, 12 tags attached to the human body. Okay, so we didn't put the tags on the shoes. The reason is that or head. Okay, so if you can do that, so you can have a full body. Okay, but then probably the positions of these 3 antennas need to be adjusted. So all the tags will be covered by at least 1 antenna. Okay, and then child is doing different activities like squatting, boxing, kicking. Okay, and these are all built with the off-the-shelf RFID devices. And this little black box is Kinect. It's a video camera Xbox. Okay, so for ground truth. So here are some screenshots of some activities. Okay, so squatting and walking. So you can see, so in the middle are the results obtained by cycle pose. Okay, so on the right is the ground truth, and on the left, the red skeletons are obtained by RFID-Pose, the first system that makes it work. So you can see the cycle pose, this skeleton pose is very close to the ground truth, closer to the ground truth. And we also show the in the middle, these 2 figures are the error distributions. Okay, position error. So it's in the range of this. So it's interesting to see that there's no free lunch. So if you want generalization, if you want your model to work well for some untrained, new, unknown subjects, okay, then the sacrifice we made is that when we apply this this right curve, it's the cycle pose. Okay, so when we apply this to some trained subjects, the performance, the error is a little bit bigger. Okay, so it's increased from 3.8. That is the previous RFID-Pose approach to 4.44. So it's larger. But when we apply this trained model, cycle pose trained model to an unknown, a new subject, untrained subject, then the error is reduced from this 7.66 to 4.88. So that, yeah, so basically there's a trade-off there. Okay. Okay, so the last piece of this talk is how do we adapt this to different data domains? Yeah, we call it data domain, actually just different locations. Okay, so for example, we train the model with data collected from my apartment. Then we want to apply it, the model, with little change or some small change in a computer lab, in a corridor. Okay, so when the propagation environment is changed, what shall we do? Okay, so as shown here, for the RFID-Pose system, positions 1, 2, 3 are trained, so you get good performance. But when you apply this trained model to an untrained location, new location 4, 5, 6, then the error is much bigger. So how do we deal with this? So we call it the data domain, the data collected from different location, okay, different position. So one example is shown here. So that is same activity but different locations. Then you can see the collected real data is very different. Okay, so and yeah, so the difference due to two yeah, it can be explained, okay, in two like can causes. Okay, so the first one, imagine just consider this case. So two tags attached to the body and two positions P1 and P2. So when the person is standing in P1, okay, so tag 2 is the distance from tag 2 to the antenna is R2. The distance from tag 1 to the antenna is R1. So tag 2 is closer to the antenna. Okay, and then usually it will have the tag 2 response will have a higher received signal strength. And then the reader will usually, when the reader interrogates multiple tags, so a tag with a clean channel with a higher RSS will be sampled more frequently. So if we train the model at the location P1 here, then the model will be trained with more data, collected phase data from tag 2. Okay, then then this person moves to P2, then we apply the data, the trained model, okay, to do the inference for this new position. Then, but in position P2, tag 1 is closer to the antenna, and tag 1 will be sampled more frequently. So basically, we are training the model using more data from tag 2. Then for inference, when this guy moves to a new position, then for inference, we are using more data from tag 1, okay, to do the inference. So basically that will cause this performance degradation. Okay, and another reason is this is that we can imagine. So there's a multipath propagation in the environment. So then we can imagine this space vector. Okay, so the motion of this tag. Okay, so it consists of two subspace vectors. The first part is a static vector, so that it represents all the effects of the environment, multipath environment. That does not change during this measurement time. Okay, and then there's another RD, a dynamic vector that's caused by if you're waving a hand that by the subject's movements. Okay, so yeah, so and the sampled phase is affected by both vectors. Okay, so as given here. So if the antenna is placed, the movement of if the position of these antennas change. So suppose you have position 1, then you go to position 6. Then the relative position of these antennas are different. So that will change your this RS. Okay, so that will cause a big difference in the sampled data. Okay, so how do we deal with this, right? The system is almost the same as the RFID-Pose, the first part of the work. Okay, so we adopt this meta learning model. Okay, so to train this deep learning model. Okay, so the idea is that meta learning is called a learn to learn. Okay, so basically the focus is more on the learning algorithm itself, so it can give you the better generalization performance. And so basically we can put through this meta learning training, then pre-trained model, then the parameters will be well initialized, okay, at some very good location. Then when we apply this model to a new environment, we just collect a few additional examples, a very small number of new data, okay, from a new location, and use that to fine-tune this model, okay, parameters. then eventually we'll get good performance. Okay. And the system works like this. So one trick here is that we originally have 4 data domains, 4 locations. Okay, we collect data from 4 locations and use them to train the model. But we introduce a domain fusion algorithm. So that is to randomly select data from these 4 data sets, okay, to form a new data set. So that is equivalent to we are creating a larger number of faked new domains, okay, from these 4 known domains, okay. Then we use the Multimodal algorithm to train the data, to pre-train the model, okay. Then when applied to a new domain, then we collect a few new examples, and apply this a few shot fine-tuning. Then eventually it will work, okay. Yeah, I think I'll skip the details. So this is the experimental setting. So we have 8 different locations or different domains. Okay, so D1, D2, D3, D2, D7 in the lab environment, and D8 in the corridor. Okay, so this corridor environment is very different from this lab environment, and we tried 5 different people. So the yeah, so you can see the in this figure is the errors. Okay, errors obtained from different domains. We have these 8 domains, D1 to D7, D8. So the blue bars are so basically we use D1 through D4, these 4 data sets to train the model, and then we apply it to D5 to D8. Okay, so you can see here. So if we apply the trained model to D1 to D4, the performance is quite good because we use the data to train the model and then apply the model to the same environment. Okay, then if we apply this trained model to D5 through D8, the blue bars, the for untrained environment, very different environment, then error will be much bigger. Okay, but then we apply this fine tuning. So basically, we collect new data from this unknown D5 to D8 different locations, but we don't need much, just a little bit data, and use that to further fine tune the trained model. Then the errors are given by these red bars. Okay, you can see that the error is greatly reduced. Okay, and we also try in the lower figure show the effects of fine tuning on different kind of activities. In this right hand figure, upper right figure, it shows the fine tuning on the different data domains. Okay, so we tried 1 shot, 2 shot through 5 shot fine tuning. So each shot is like data collected in 6 seconds. Okay, so you can see like we don't need too much new data. Okay, so it's just maybe 4 shots will be sufficient, and the error is reduced from 6.27 to 3.96. It's about 36 percentage of reduction. Okay, so this is like suppose you get your new iPhone, okay, iPhone 13, okay, then you want to enable Siri, okay, on your iPhone. Then, so basically, there's a fine tuning or training procedure. You're asked to by your phone to read a few sentences. Then once you read it, then through this recorded the sentences you read, then the Siri can learn your accent, your habit, your features. Then it has a already pre-trained model. By using this new data, then you fine-tune the model, and it works. It's tailored for your voice, your habit. Okay, so it's similar. Okay, so in this talk we talk about RFID for human pose tracking. It's a good application, important application. And RFID is a promising technology. And we talk about how to use vision assisted. So we make use of the video data in the training of the model. Okay, but then during operation, then we don't need video data. So there's no concern of like a privacy or security. Then we also talk about adaptability, generalizing your model, the trained model, to different people or different operating environments. So the advantage is that the system can be easily deployed at different locations, different environments. You don't need a lot of work on collecting new data or retrain the model. Okay. Actually, this is important not just for this human pose estimation, but it applies to like a channel estimation, for example. There are a lot of interesting work on using deep learning to estimate what is channel. Then what if the location is changed? What if the channel in the propagation environment is different? The frequency is different, right? Or what if, yeah, yeah. So actually, I think it works there too. Yeah, so it's a good solution, this meta learning approach. Yeah. Thank you.
Thank you. We should thank you a lot, okay, for really an insightful talk, and the topic is very interesting indeed. So, well, question from the audience. There is one that is on the chat, says, depending on the application, what the position error is tolerated, could be tolerant?
Yeah, that's a good question. The answer is I'm not sure. So it depends on because we haven't we have not been working on a specific application yet. So most of our work is on how to capture the data, then how to deal with the noisy sparse data, and how to recover this human pose. So then the next question related to the next problem related to your question is, what are you going to do with this recovered pose, right? So a student of mine is working on this. So we are developing recognition or classification techniques. So once you have this 3D pose in motion in continuous time, then we feed this into a classifier. Then we can recognize, oh, it's a squatting, or it's a boxing, it's a walking. Then this can be used to control like your video game or your something. Then up to that stage, then we probably need to know what kind of error is good enough. Yeah.
I'm thinking about military applications. So
Yes.
in military application, if they want to know what this potential guy is doing inside the room, then maybe the accuracy that is requested will be high. Other than that,
Yes.
maybe not. But we saw the results are amazing. Okay, so the amount of error is really small.
Yes.
Okay, more than what I expected.
Yeah, it's currently the error the median error is like a few 3, 4, 5 centimeters. Yeah. So
yeah.
in comparing to the human body, I think that's tolerable. Actually, I got the idea from a friend. He's a professor in system engineering. So they were considering the problem that it's like in a factory. Okay, so you have workers working on the product line, like working on building like bombs or weapons. So they have a video camera watching the workers. So in case they are making some dangerous actions or unsafe, cause risk to. So yeah, he was talking about that problem. I think that could be also be a problem application for this. Yeah, but so far we haven't tried. We're considering some things like a video game. You want to control a video game or something.
Yeah. Good. A question, curiosity from my side. What do you think that will change if it is not humans? Okay, so if you would like to pose track for animals, do you think that a lot of stuff will change or not? Definitely, whatever is trained for humans, I think that it will not work for animals. Okay, transfer learning will not work. But if we train over animals, Do you I have no idea. Okay, but do you have any guess if this will also work, or you will meet new challenges? Well, definitely, maybe we have to also get some data from some I don't know someone who deals with animals. How many bones? We really don't know. Okay,
Yeah.
but well, this is a curiosity. Okay, do you think that it would be transferred and the results could be obtained as well?
Yeah, that's a good question. So I think it will be hard to transfer from human to animals, but from animal to animal, maybe it may work. Yeah. So actually, I think because our area, this wireless communications, wireless networking is becoming quite crowded. So that's why I'm trying to explore other fields. One problem, one area I'm also interested in is to apply this wireless technology, sensing technology to agriculture, as you mentioned, the animals. And we have done some work on using this to for like a store the grain, store the wheat. So how to use this RFID signal to detect moisture level, mildew, or temperature of you have tons of stored grain or corn. So how do you apply this? I think this precision agriculture or application of wireless to agriculture would be maybe in the next few years you'll see a lot of papers. Yeah, it would be a hot topic.
Very interesting.
Yeah.
Luca, do you have any question? I saw you turned on the video.
Yeah, I was just thank very nice talk.
Yes, we hear you.
And yeah, I had just curiosity. Of course, as always, some let's say some of the things you are detecting are easier to be detected. So apparently, the working one was one of those. So was just wondering if you could elaborate a bit on why that's. What are the reasons for that? If you have any idea about that.
We haven't thought about that, but I guess it's because some activities, it's the location of these tags. We have 12 tags on the body, so yeah. For example, if the tag is in this vertical position, so this is your antenna, this is a tag, then the response will not be very strong. So sometimes you miss a lot of examples from that tag. But if it's like this, the tag is like this, facing the antenna, then you get a very good, clean, strong signals. So different activities may put the tag on some joints in a certain different angle or location. So, but it could help if we have more antennas around like an immersive kind of reading around the human body. That will work. Wow, yeah, that could be that's what I can imagine. Yeah, so yeah, dope.
Thanks a lot.
Okay, so thank you, Luca. There are no more questions from the audience. No questions. Then we come again to thank you for the interesting talk. Okay, really thumbs up. Okay, so very interesting. We will be sharing the recording with the people at CSIM, okay, over our YouTube channel. And if they have any question, they will contact you directly.
Yeah, sure. Yeah, I'd love to answer any questions. Yeah, feel free to contact me. Yeah.
Very good. Well, so thank you again, and thank you for the attendance, and see you in next CSIM seminars. Please stay tuned.
Yeah.
Thank you.
Thank you so much for having me. Yeah,
Bye-bye.
really appreciate it.
Thank you.
Everybody, bye. Thanks a lot.
Bye. Thank you.